So, I'm Kevin Brown, and I'm a PhD student at Stanford. And I'm going to talk to you about some of the work we've been doing over the past few years developing a product called Delite in Scala. And it's a few of us at Stanford and then collaborating with the Scala team at EPFL. So the big problem with data analytics space is, I think sums it up, you can say it in this long line right here, is that people doing data analytics are mostly data scientists. Data scientists are not computer scientists. And even if they do know something about programming, there's a very big gap between competent programmers and programmers who understand compiler details and how to get really good performance, right? Because you start talking to these guys about, Hotspot has a megamorphic inline cache, and they glaze over, and they have no clue what you're talking about. So obviously, we can make this simpler. We can write libraries for them. They use the libraries. All the magic is under the hood. This is great, but traditionally, libraries, they really add a lot of overhead to your runtime, and so you don't get the same performance that you would get if you actually wrote it by hand in a low-level implementation. And whether you did it yourself or use this library, data sizes are getting bigger and bigger. CPU speeds are not getting faster. And so really, the sort of single-threaded bottleneck is huge, right? There's just so much you can pump through one core in a reasonable amount of time. So really, in order to do this well, we need to be able to run on modern hardware, and we need to be able to do it very efficiently. So looking at what modern hardware is, right? Everyone has multi-core CPUs these days, but then there's a huge explosion of accelerators coming out. There's GPUs, they've been around for a while. FPGAs are becoming popular. You've got like MPEG-4 decoders in your phone. There's a lot of them now, and there's going to be more and more. And finally, we can put these all together in big clusters. But if you really want to program these things efficiently, first of all, there's a different programming model for every single one, and they're all very low level, and they're all very painful. So, for multi-core, you've got threads. For GPUs, you've got CUDA. For FPGAs, you've got Verilog, and for clusters, you've got things like MPI and Hadoop. And really, this is just very, very far away from what people want to express, because they're trying to, solve their data analytics problems at this very high level. They're scientists, they're biologists, they're statisticians. They don't understand this. And so the question is, how can we bridge this gap between the high-level applications and the low-level hardware? So obviously, let's try a language. So let's look at general-purpose languages. Look at Scala, look at, pretty much all the successful ones. Can we do this? And the short answer is no. It's really been tried in basically every language. And the universal consensus is that there's just not enough semantic knowledge that the compiler has to be able to do these kinds of transformations automatically for you. So if we can't do a general purpose language, let's try a domain-specific language instead. And what's interesting is, I think most people, when they think DSLs, they think high productivity. They want this pretty little library. You can write everything in 2 lines of code. It's easy to read. It's easy to change. It's great for developing things quickly and getting it right. But what people don't appreciate is that with the sufficiently well-designed DSL, you can actually also get very high performance. And we actually showed that you can have DSLs that match or exceed the performance of hand-tuned implementations, written in things like C++ using pointers and all the tricks that imperative programmers do. And finally, once again, by using this high-level semantics of DSLs, we actually have a chance to take a single application source, automatically transform it to run on all these different architectures efficiently. So our vision is essentially, as I said, between the applications and the hardware, we're going to have DSLs, and the way we're going to make those DSLs actually efficient is writing a compiler for those DSLs. But then the big question is, okay, you need DSLs, you need to have a lot of them. How on earth are we actually going to scale this? I think contrary to Eric's opinion, writing a compiler is not that easy. If you want it to actually generate efficient code, maybe writing a correct compiler is not that hard, but writing a high-performance compiler actually takes a lot of time. So what we really need is a way to say, okay, the DSL authors are our expert parallel programmers. How can we make their lives easier to quickly spit out high-performance code? And the way we really want to do that, of course, is to make compilers simpler by providing frameworks for you to build them. And then once we have that, then we can have the expert programmers, those are the DSL developers, generating very high performance code, and then all the users use them, and you actually get this, high level yet performant code on these for these domains. And so the next question is, okay, I want to build these DSLs, but I need to make it productive for users and developers of the DSL. So how can we make a domain-specific language that's as productive as writing a simple library in something like Scala, and as performant as writing optimized parallel code? Which means basically for users, it's got to be high level, it's got to be composable and debuggable, all those things that they expect. And for authors, it actually has to be, take a reasonable amount of time to construct and extend and maintain. So our approach is essentially embedded DSL compilers. And as you can probably imagine, since you're here, this is embedded in Scala. And we use a metaprogramming technique called multistage compilation to essentially take these Scala applications, build an IR of the program, and then run our compiler as a Scala library and generate new code that can target different platforms, like CPUs and GPUs. And if you're interested in this, there's actually another Scala project called Lightweight Modular Staging, which essentially Delite is built on top of that lets you do this metaprogramming much easier. So it essentially allows you to define, what types you want to evaluate now and what types you want to evaluate in the generated code. And then it provides you a common framework for defining how to generate code and how to schedule code and how to apply optimizations. And then Delite builds on top of that with all the parallelism stuff that I've talked about. So in summary, same vision, but now I'm just going to wrap all these DSL compilers in a common substrate, and that is what we call Delite. So now I quickly want to go over some of the DSLs we've actually developed using this technology, so you can get a sense of what you can do. So the first one is called Optical, and it's essentially designed for machine learning linear algebra. It's got basic things like vectors and matrices, what you would expect, and everything's implicitly parallel. So you've got summations and maps and vector constructors, gradient calculations that are all run in parallel. So I think in all these situations, it's best just to kind of actually see what it looks like. So this is k-means clustering written in Optical. It's always nice when code can fit on a slide. So, at high level in k-means, all you're really doing is you're taking every sample in your data set, computing its distance to every centroid in your means, and then you group the samples by the current mean that they're closest to, and then you compute new means by averaging all the samples assigned to that group. And of course, you repeat this until the k-means stop changing. So as I said, it's very simple to write. And also, we can fuse this map rows calculation with a distance in the middle. And correspondingly, we can also fuse this outer thing, so you don't have to group and then map. You can actually do this whole thing as one traversal of the data set. And the end result is very ugly code that looks like this. But you'll see that a lot of good things have happened, right? There are no matrices or vectors or anything. There's just raw arrays. There's no functions. They've all been inlined. And all the implicit parallel traversals have been chunked into these explicit while loops with very first-order low-level code. And we can do it in Scala. We can do it in CUDA. And of course, the high-level point is that code like this is something that the next stage compilers can chew through really easily. There's no abstractions for them to get bogged down by. So this is essentially, at the end of the day, what we call abstraction without regret. That we start with these DSLs, we generate very low-level target code, and then it actually runs as if you had written it this way instead of the other way. So the next DSL is called Optical, which is for querying in-memory collections. It's very similar to LINQ or SQL as the oldest language of this type. And essentially, just like those languages, the idea is to have a query optimizer on the front end and then use Delite to do low-level optimizations under that. And what I think is really useful for this language as well is not only can you do it to compute simple statistics like you see in these old-style benchmarks of queries, but you can do a lot of data transformations And once you do that, you can combine that with something like Optimal, which we just showed, to, as a pre-processing step. So I can use Optical to transform my data into, say, a matrix of double format that Optimal expects, and then use Optimal to actually do the quote-unquote real learning that I want to do. So now here's an example of everyone's favorite benchmark for SQL, TPCH query 1. So it's basically, you have this table of line items. You filter them by some ship date, you group them by their status, and then you reduce every group with a lot of statistics. And so first thing, very simple, but something that a general purpose compiler will not do is actually lift the constructor of the state out of this loop. And the reason it won't do that is because, under the hood, this is calling new class, blah, blah, blah. And new is an effect, and the compiler can't just decide you didn't want to do that. But we can. The next thing is, so you're computing many reductions here, and we can actually fuse that into a single loop that will compute all your reductions in one traversal and just hand you off all the results in a tuple at the end. And finally, we can fuse the where group by select into one traversal as well. And now also you'll see that we have these notion of records, which are essentially like structs in other languages or tuples with names, whatever you want to call it. And they can be named or they can be anonymous, but basically they're structural types that the user can define. And so here's line item defined by the user. You can see line item is very, very long. But what's interesting is even though there's, I think, 16 fields here, the query I just showed you uses half of them. And using our compiler, once you compile that query, it can automatically just determine that you didn't need the other half of those fields, and it will just kill them off for you. And so you don't actually have to have those fields at runtime. All right. So then, last interesting DSL OptiGraph is essentially graph analytics. It's inspired by another DSL called GreenMarl, which was developed by another student at Stanford. And similar to, it's not that dissimilar from a lot of other graph languages. You've got graphs that are directed or undirected, you traverse nodes and edges, you store things on the nodes and edges. And what's really interesting, though, is that the language does a lot of work to optimize the internal layout for you. So if you've ever done a lot of graph analytics yourself, you know that how you lay out the graph in memory actually has a lot of impact on how well you can traverse it. And so the OptiGraph will do a lot of this for you. So here's OptiGraph syntax for triangle counting, which is everyone's favorite, very simple graph app, which essentially, so a triangle is defined as, if a neighbor of your neighbor is also your neighbor, that's a triangle. So here we have, you can do traversals and reductions over nodes or edges. So this will essentially sum all the counts. And then, of course, once you do that, you can traverse your neighbors. And then we also have these interesting, so this function common neighbors, we have a few of these which are essentially, they look like convenience methods on neighbors, but it also turns out that if you want to do applications like this efficiently, summing up counts is very, very cheap, right? So really all the work goes into things like this, is figuring out what are your common neighbors. And so we don't want the user to write that. We abstract over it for you. And then also, like I've said before, since in this case I don't really care what your neighbors are, I just care how many of them you have, we can fuse get the common neighbors and then call size into one loop that just doesn't even store the neighbors themselves, you just count them up. And the end result is performance that is very comparable to handwritten code. So now I want to kind of go into, you've seen those DSLs, how we could actually implement those DSLs in Delite, get a lot of features for free, and how you could potentially write your own DSL. So Delite itself at a high level has essentially two pieces. We say operations are defined in terms of parallel patterns, and these patterns are things that most of you are probably very familiar with. They look a lot, they're like Scala combinators, data parallel ops from other places, map, zip, filter, etc. Of course, they're composable and nested like they should be. And also you implement your data structures in terms of relatively restricted primitive data types. So we have, the basic Scala primitives, we have arrays, you can build structural types on top of those. So then your job as a DSL developer, when you use Delite, is just to, of course, you define your domain data structures and domain operation abstractions, and then you lower those into Delite parallel patterns and Delite data structures, and then Delite in turn lowers that to target code for Scala, C++, CUDA, everything else you want to generate for. So the way you actually do this in code is you start, we'll say, I want to build a simple vector language. It's going to be very simple, but it's fine. So we first define a type vector, which as you see is completely empty. It's essentially just a name for your type. It doesn't really do anything. And now once we have that type, we can define methods on it. And so we can define a max method on vector. And if you look at the implementation, you see that we're not actually computing max. We're just creating an object, vector max, that's going to represent that computation in RIR. So the next thing we, of course, have to do is actually create that object. So it's just a case class. And the interesting thing here is that it actually extends Delite op reduce, where reduce is, of course, one of the Delite built-in parallel patterns. And so basically, if you do this, all you have to do is define the reduction function, and Delite takes care of everything else for you. Because we know how to generate reduces for multi-core, for CUDA, et cetera, et cetera. And of course, similar to operations, you have to define your data structures. And so in this case, I've just said a vector is nothing but a struct of a data field, which is an array, and a length field, which is an int. And similarly, Delite generates structural types in all the different target languages. So the next thing you can do is you can define your own domain-specific optimizations on top of this. So I've switched from vectors to matrices just to keep things interesting. But now we say, okay, essentially, it's just pattern matching like you see a lot in Scala programs. And this one is just looking at, okay, if I have AB plus AD, I want to rewrite that to A times the sum B plus D. And so all you do is you have a case statement which matches on the matrix times. You say, okay, I've now matched that pattern. And I said I just returned the optimized result. Whereas the default thing of matrix plus is, of course, just to return a blind plus. But now I've returned this other times that has a plus in it, and it replaces the other thing that used to be there. And so finally, you just wrap this all together in a pretty box. You say, my DSL is a trait that includes vectors and matrices. So now I have my very simple linear algebra DSL. And then when people want to write their apps, they create a trait, my app, extends my DSL. They define a main method, and they can call all of your defined operations in it because, of course, the trait's from extend. And once again, because they're using Delite, all these operations are implicitly parallel, run everywhere you want them to. So to summarize, the really key advantages of Delite over using just building your DSL from scratch is, parallel patterns are first-class citizens, and that is really where a lot of the magic is and how we can generate code for all these parallel targets, and also how we can make your life easier so the DSL developer does not have to worry about parallel programming nearly as much. We already have code generators implemented for many languages. We can currently generate Scala, C++, OpenCL, CUDA, and clusters thereof. And we build on top of this existing Scala LMS library, which not only are we using, but other people are using. And the big benefit of LMS is that it does a lot of systematic removal of abstraction, which is how you can write high-level code, strips all the Scala features out, and get low-level code. And we provide a lot of optimizations that you might care about in your language for you out of the box. You extend Delite, and you get these for free. And as you saw in the examples, Fusion is one of the bigger important ones. We also do array of structure array transformations. We do code motion. We do dead field elimination, common sub-expression elimination. There are a few more, but those are the highlights. And the final big benefit of using a common framework is that, of course, what you really want to be able to do is take multiple DSLs and compose them, because that's how we make big applications. And if you build all your DSLs ad-hocly, this is actually a very hard problem. How do you compose the output of this DSL with the input of the next one? You end up using bash pipes or something. It's not very efficient. But with all these DSLs using Delite, we can actually compose them in one application and communicate through memory. And so you can actually build complex pipelines where you start with unstructured text, you clean it into something structured, you query it, and then you apply machine learning or graph analysis to it until you get your final answer. So that's sort of the first half of here's the light, here are the DSLs. And now I'm going to essentially jump into case studies on what applications we've looked at that did not come from us but came from other people, how we've used Delite to solve their problems, and what hopefully can be used going forward. So the first thing I want to talk about is called Ringo, which at a high level you can think of it as just, I want to do graph analytics, but I have a table. So what do I do? So this was originally designed by another group at Stanford, the SNAP team, by Yuri Leskovec. And essentially what they have is they have this sequential C++ under the hood library for graph analytics, and they bolted a Python top end in front of it to make things easier for users going forward. And so their problem was, well, I have graphs, but very few people actually have a graph that they can hand you. They have something else that you can infer a graph from. And so the typical solution to this is, okay, well, write my little Python script, let it run for a few hours, get the new result, and then pass that into the actual analytics engine. But then what they found is, well, they have these really big data sets. Python is really slow. And what they ended up doing was, parsing it in from disk took hours to run. They didn't want to redo that. So they just left their Python process open continuously and, prayed and hoped that it never crashed, because then they have to start all over again. So that was not the greatest solution ever, but it worked for them, I guess. So the insight here is really, what I've told you is not dissimilar from just taking Optical, taking OptiGraph, and composing them in a pipeline, right? Optical consumes tables. It can convert those tables into an edge list, and OptiGraph will do your graph analytics for you. And so really, if you want to convert tables to graphs, there's sort of two use cases that you have to care about. The easy one is, two of the columns in that table implicitly form an edge list. So you project them out and you move on. That's great. But the perhaps more common case is that you really actually have to infer edges from the table because it's not in that format. So you might say, I want to infer an edge for everything that satisfies some distance property that I define. So we can see how that can actually be written in Optical. So this example is you start from traceroute logs, which are essentially, just every row is, a timestamp and a bunch of metadata and then a bunch of traces. And the trace itself has actually been sort of stringified and inlined into the log. So it's implicitly a nested table. It's all been flattened into strings. And so then one of the fields is actually, this IP, next IP, next IP, next IP. And what I want to build is a network graph. So what I really need to do is infer an edge between every pair of IP that I see in the log. And you can actually do this in very few lines of Optical. So we can parse the table from disk by just defining what your separators are. And then from there, we just need to then parse the nested table of IP addresses into a table. And then the sort of core of it is right here, this hops .ip, hops of i+1.ip. That's what's saying, every IP in my list, take this one, take the next one, infer an edge between it. And so the result data structure of this is a table of pairs. And of course, every pair is implicitly an edge in my graph. And then we do a little extra post-processing on it. And so we actually throw away all the edges that didn't appear very often because those are probably not that interesting. So what we get back is essentially an edge list of edges that we think are actually real in a network graph. And like all pictures, I must show you that this is efficient because everything fuses together nicely. And so, but you need a few more things to actually really make this run fast. We can do all these things in Delite. And one interesting thing that I have not talked about before is that, it's not just about high performance in memory, it's about high performance from disk too. And of course, in any kind of application like this, reading your text from disk is actually the most expensive thing. And so But fortunately in Delite, our file reader component and the rest of our in-memory traversal components are actually all based on the common parallel substrate, which means we fuse across them. So you can actually read rows from your file, parse it, filter it, etc., and dump it all into the output in one traversal. So very simple example, read every line of the file, filter by something I don't care about. That's one traversal instead of two. And finally, of course, we need multi-DSLs to work together for this to make sense. And the obvious way you could do this would be to write both programs and serialize the intermediate result through disk, and that's fine. It works perfectly well. But with Delite, you can actually also pass things in memory between DSLs because it is all one system. And we do this using a feature called Scala scopes, which are essentially, they're like function blocks that you've seen, except the DSL traits are actually injected inside that scope. So if I'm in an optimal scope, then suddenly all the features of optimal become available to me. I leave that scope, they're no longer available to me. And the end result is that we can do this graph transformation very, very efficiently. So this is a 20 gigabyte traceroute data set from Akamai. And you see I wrote it using like standard Scala library using combinators. So essentially similar code to what you saw, but turn everything into maps and filters and reduces. And it took an hour to read. And then just single-threaded Delite using our optimizations, we're down to 15 minutes. And then since we can actually do parallel I/O, we can actually scale really well, and you can read this whole data set in about a minute. So the next example application is called MSMBuilder, which is work from Vijay Pandey's group at Stanford, which they do a lot of biophysics simulations, and you've probably heard of Folding at Home. It was pretty famous a while ago. It's the same group. So what they really wanted to do was say, well, we decided that Markov state models are a really powerful way to do molecular dynamics, but of course biologists don't want to have to write all this code, so how can we build them a nice library for doing this? And similar story is like the one they did by themselves was pretty complicated. So basically they wrote the whole thing in Python, decided it was ridiculously slow, profiled it, figured out where the time was going, and rewrote those pieces in C++, and then did a foreign function call to transition between. So we said, well, let's not do that. Let's just replace this whole thing with single source optimal code. So that way, you can actually reason about the whole program in one nice little package, and it should be just as fast. So we've found that this is actually a very non-trivial program to get fast. And one of the interesting things is that most systems that you'll see, if they target GPUs, they will only generate parallel code for one, say, loop in a loop nest. Essentially, you can't have multi-dimensional parallelism and actually exploit all that parallelism. You're going to throw away most of it and just do one level. But unfortunately, for this application, that is just not sufficient. It will be horribly, horribly slow. And so, but fortunately in Delite, we actually created an analysis where we can automatically go through your multi-dimensional parallel operations and figure out the best way to run all those, exploit all the levels of parallelism at once on the GPU. So that way you get much more parallelism available to you, and it runs much faster. And then on the CPU side, it turns out that their C++ code they wrote was actually really, really smart, like well done. And they were actually using, SSC intrinsics to really optimize their code. And what they were actually really trying to do was they had a matrix multiply, but it was very weird matrix size. It was actually 3 by something. And so they decided that they can actually, hand write a 3 by n matrix multiply much more efficiently than you can use a general matrix multiply library. The obvious trade-off is that it only works on 3 matrices. So in order to sort of get close to this, we have Optimal generate specialized code for small matrix dimensions, whereas the default is back to calling BLOS, which is what everyone does. So if you look at the performance here, you see, so out of the box optimal doing nothing special on the matrices whatsoever. It's already 300 times faster than Python. It's pretty fun. Then you ship your matrix multiplies off to BLOS, and you get about 2x, which is not bad. And then you specialize the matrix multiply using these vector intrinsic instructions. Now we're at 3x. And the last bar is the hand-coded thing that they wrote. So we're actually very close to what we consider super hand-optimized performance. But this is not the end of the story. This is multi-core. We approached what they did after a long time. But as I said, we can run on the GPU. And while it is very hard to generate a CUDA kernel for this application, once you can do it, it runs really well. And so, you wrote your optimal program. It takes no extra effort to switch from CPU to GPU execution. And the big high-level picture is pretty fun. Like, they started with Python. They switched to C++ with ASMs, and they got 1600x speed up. That's cool. You switch to a GPU, and now you're looking at almost 3700 times speed up. So not only do you learn that most programs are really, really slow, but you learn that you can spend a lot of effort writing the slow thing, porting the the expensive parts to really, really efficient code, but you're still, you're going to be stuck to what you were with what you did. They can only target CPUs, and it turns out their application was really very GPU friendly. So you use Optimal, you can run it either place for free, and you can get much better speed up. All right, so the last application is called Deep Dive. So this is a inference engine developed by Chris Ray's group at Stanford. And it does a lot of, essentially it will read the web or read financial documents. They also do a lot of work on reading research papers, and it builds a model for these things that they read in. And it's actually pretty cool and sophisticated. So this example I'm showing you here, they're reading research papers, and they want to parse tables in the paper. But what they figured out was that it's actually not sufficient just to read the table in isolation. You have to read the table, read all the text surrounding the table, and put those two together to actually build a better result. And so they developed a lot of algorithms to do this kind of work, which is I'm not going to talk about because I don't really understand it, but it exists. So one of the big things they did to make this fast is they invented this thing they call hog wild updates. And if you boil it down, it really means if you look at a lot of ML programs, you can essentially, it's up to you how frequently you want to update your model. Right? Because a lot of these programs essentially, while I'm not converged, take the old model, go over the data set, compute the new model, repeat. And so option one is sort of the sequential way. You can update the model every iteration, but now you have loop carry dependencies, so you can't parallelize that loop. So while this actually converges really quickly in terms of number of iterations you have to do, it is fundamentally not scalable, right? You can only run sequentially. So what a lot of people do instead is they do this batch version, where essentially you hold off updates, commit them in large batches, which allows you to parallelize over that whole batch. But the end result is that it actually takes many more iterations for your program to converge. So the end result of this is that it's actually really hard to say which algorithm is faster, for a given core count. Because one is using more resources, computing every iteration faster, but it takes more iterations. So which one actually wins? And so what they did was they came up with this kind of semi-crazy hybrid version, which is to do the sequential algorithm, but just let the writes race. And it's interesting because they actually found that this works. It produces correct answers, and not only that, but it really finds you a nice sweet spot in the space between scalability and convergence. So they do it hog wild, and they get better scalability sequential and better convergence rate than batch. And so actually, if you compare all three on a given core count, this one actually tends to do the best in terms of total execution time. So what we wanted to do is take all this that they've done, once again implement it in our framework. And so we started with something very, very simple, which is stochastic coordinate descent. You can see it takes all of 4 lines of optimal code to write the main chunk of it. And so we ran it, and we found something interesting, which is, so this is a 4-socket machine. 10 cores per socket. So this first bar I'm showing you is just, scaling up in the socket. And it does really well. 8x on 10 cores, great. But now we have all these other cores that we could use, and not so good. And it's completely dead, right? And if you look at it, the underlying cause of this is the fact that these big multi-socket machines, they have different memory regions, right? And if you want good performance in these machines, you actually have to care where you allocate your memory. And you have to read the memory from that region and not the other regions. And so it's actually not dissimilar from distributed programming. You have many regions of memory. You have to touch local versions and not remote versions. But unfortunately, there's not great ways to express this in most shared memory architectures. Like, you really can't control this to the degree you would need in the JVM. But as I alluded to before, we're not tied to the JVM at runtime. We can also generate native code. So there is a solution to this. And what it basically boils down to is we need to be NUMA aware on our loads and stores. So in order to make this scale, you actually have to, instead of allocating the data set all as one data structure, one array in memory, you need to partition it and so that you allocate an array in every memory region and chunk it that way. And then, of course, make your threads read the right pieces of memory. And also, similarly, most applications don't have this issue, but because we're doing this interesting hog wild updates, you have to care a lot about your stores as well, because the stores are actually essentially random and they cause a lot of cache coherency traffic across the sockets. And so you actually kind of get bogged down in coherence traffic if you don't do this very carefully. And the insight is basically that you can take kind of a hybrid approach where you update frequently within a socket and update less frequently across sockets. And so it, once again, sort of plays this trade-off between frequency of communication to improve convergence and scalability. And the end result of this is that this is the same app, similar picture, except now it actually goes past 10 cores. And we're getting over 30x on 40 cores. So it all actually works very nicely. All right, so that is I did very well on time. So the conclusions I have are basically, there are several groups of us collaborating at Stanford who are trying to get their apps accelerated. There's a lot of interesting research areas here, and I think there's a lot of availability for corporations and other people to also collaborate and try to use this and make their systems run faster. The other sort of highlight was that, as you hopefully saw from these case studies, we can do a lot of things that most other systems who are on the face of it similar to us can't do. We can do very aggressive fusion, parallel I/O, multi-dimensional GPU cogen, NUMA-aware allocations. And finally, that you put all these together, and we really do have very good performance to any other alternative solution you could find. All right, so thank you. Questions? Yes. So we are in pretty close contact with Oracle. And I think, basically, obviously, we suggest things to them. They take it under consideration. Seems to be the theme of the day. But so I do agree that a lot of things could be much nicer. Communicating with native code being one of them. It's very painful to transition between the JVM and the GPU right now, of course, because the GPU has to be native. So the nice thing about Delite is that we paper over that for you. The downside is that it took us a lot of code internally to make that work. And so, yeah, if anyone can actually make that better and actually good performance, that would be wonderful. Similarly, a lot of other things like, say, you can't allocate arrays of non-primitives in a flat way on the JVM. That is also from a performance standpoint, very annoying. And we've worked around it by doing structured array transformations. So we only allocate arrays of primitive types. And if you declare an array of a structural type, we flip it and just emit arrays of all the fields instead. And therefore, we get good performance. So yeah, the summary is if people can implement these in the JVM, I would love that. But we have sort of figured out ways of getting around that by having high-level compiler transformations. Yes? Mm-hmm. Sure. Yeah, so it's essentially, right, so the high-level idea is, say you just have two nested loops. They're both implicitly parallel. And so most people will say they'll parallelize the outer one or they'll parallelize the inner one. They won't do both. But what's interesting on the GPU is the CUDA program model actually has multidimensional support built in. So you can implicitly essentially transform nested loops into a multidimensional iteration space. And then once you have that, the CUDA compiler will translate that onto all the GPU hardware. So essentially what we do is we start with your nested parallel patterns, and then we do an analysis which decides essentially what nest we should assign to each domain dimension. And then once we do that, then we generate CUDA code, which is, essentially launches this loop nest in dimension X and that loop nest in dimension Y. And the result of that is that X and Y actually run all in parallel, and so you get X times Y performance. Oh, so they support 3, but it's actually very simple to support N because it's really syntactic sugar. So because it's all flattened, right? The GPU itself is not multidimensional. So they take X, Y, Z, they flatten it on, size times Z plus size times Y plus X. And you can do that yourself. It was nice to use the CUDA thing. So in theory, yeah, you can arbitrary dimensional. You just flatten the whole thing. Yeah.
Related question to this. So in CUDA, you have this kind of tiling, kind of optimization,
Mm-hmm.
which is probably not accessible on your side, or is it? That's the question. Do you do like this optimization when you try to use some local memory?
So in general, that's a hard problem, obviously. But there are a few ways that we can exploit shared memory. One being so a lot of times the reuse is actually encoded in the pattern itself. I think reduce is the best example of this, right? You have local intermediate results, and so it's very simple to say I want to put this in shared memory rather than global memory. Another more complicated thing you can think of is if you have essentially a stencil application where you actually have reuse, and then you can actually decide that rather than loading directly from global memory into registers, I'm going to global memory to local memory to registers, and then the next time you just go to local memory. And so the way essentially you do that is by a stencil analysis, and decide that is this, what is the window that they're touching, and then I'll load it into there. And I think we also do it to play a little trick with allocating memory within the GPU kernel. So if you've ever written CUDA, local threads can't actually call malloc locally. So you have to pre-allocate all your memory up front and then have threads use it. So we automatically apply that transformation when you write nested maps that have allocations inside allocations. We essentially flatten that, pre-allocate it, and then use shared memory to essentially improve the access pattern from what it would be naively. Okay.